So in this chapter, we start working on stochastic differential equations. So we look at finding solutions for equations will be of this form. So we are looking for a process that satisfies a certain integral equation, really, because you have to remember that dBt is not interpreted as being a mathematical object on its own. What has a meaning is the integral of a L2 log process against dBt. So really, we're looking for a process xt that satisfies this integral equation. Xt, say minus x naught, is a certain Lebesgue integral of a process that depends on xt, a certain function of xs and s, plus an Ito integral of a process sigma sxs that depends also on the time parameter and the process itself. So the question is, can we always find solution to that? Under which condition on mu and sigma can we guarantee existence and uniqueness of the solution in an appropriate space of process? So we're going to do two things. We're going to look at equations that are simple enough for us to explicitly find a solution, and a formula for xt that is not an implicit formula. See here, this is not really a formula for xt because I've got xt on both sides. So it's just an equation that xt has to satisfy, as opposed to something like what we have here. That would be a formula for xt, and directly describe xt in terms of quantities that we understand, like the time variable t and the Brownian b of t. So we are going to do these two things: find explicit solutions for simple enough equations, and prove that under appropriate conditions on mu and sigma, a unique solution always exists. Now, what does that give us? Well, that gives us a much wider class of stochastic processes that we can use in modeling, right? Because we won't need to just say xt is a standard process with that a and that b. We will be able to look at the wider class of processes that arise as solutions of such an equation. If we know there exists a unique solution, as soon as we write the equation, we could say, I am now considering xt the process that is obtained as the unique solution of that equation. So that gives you quite a lot of modeling power. So we'll do applications to finance later on. And in finance, we'll be looking at constructing portfolio, things that are made of a certain amount of cash and a certain number of stocks. And we will be creating portfolios that match the risk structure of certain insurance contracts. And really, what we will be doing in doing that, finding a portfolio, will be solving a stochastic differential equation. What we have here will be the value of the cash part of your portfolio, and what we have here will be the value of the stock parts of your portfolio. And they will be linked together by a certain differential equation it's a stochastic differential equation, and conditions that make the portfolio match a certain risk structure, and the existence and uniqueness theory that we're developing in this chapter 6 will guarantee that such a replicating portfolio exists. In certain situations, we'll get an explicit formula for it, but not always. But the existence of it will be helpful in itself. Now, of course, these stochastic differential equations are not limited to finance at all. In physics, people call them Langevin equations, and the idea is that you can use them in every possible science. So, I mean, whenever you have a model involving, say, an ordinary differential equation, some exponential growth in an epidemic, say, if you're doing epidemiology, whatever else you're looking at, you can improve your model by adding to your standard ordinary differential equation a term here that represents some noise. So it represents some uncertainty on what you're looking at, right? The solution of such equations would be typically like the solution of an ordinary differential equation, but with some random fluctuations around the deterministic part of the equation. So this is the modeling power from an applied point of view that we will gain through this chapter. But what we're going to do first in this video is look at simple cases and solve them by hand. And the next videos will be about the general theorem about existence of uniqueness for such differential equations. Okay, so we will look at 3 examples of stochastic differential equations that are simple enough for us to be able to explicitly give a solution. So the very simplest case I can think of an equation of the form dxt equal mu txt dt plus sigma txt dbt is the case where both mu and sigma are constant processes. So the equation dxt equal mu dt plus sigma dbt, which we've already looked at, right? It gives a drifting Brownian motion where mu and sigma are just real number. So what does it mean to solve this equation? Well, it means find a process such that xt is x naught plus the integral from 0 to t of mu ds plus the integral from 0 to t of sigma dbs for all t. But the thing here is that these two integrals I can directly compute. So this equation is literally equivalent to xt equal x naught plus, well, let's compute it, it's mu times t, plus this equation, let's compute it, is sigma bt minus b naught, and b naught is 0. So that's it. This is an explicit description of your process. That is the solution process, and that's an if and only if, so this solution is the unique solution. Okay, so let's have a look at a more interesting example now. So example 2, I'm going to take the process mu txt and sigma txt to be just multiple of xt itself. So not constant, but linear. So I'm looking at dxt equal mu xt, linear in the second variable, plus sigma xt dbt, where mu and sigma are in R. And what I'm going to do is that I'm going to assume that xt is a function of time and the Brownian. This may be wishful thinking. Maybe I cannot find a process that is just given by a function of time and the Brownian and that solves this equation. But I'm going to try that and find conditions on f that might work. And maybe I'll find a process in this way. So I'm hoping to find something of that form for some f that will be c1 in the time variable and c2 in the second variable. Now for such a process, I can apply Ito's formula. And Ito formula will give me that dxt has to be dt ft bt dt plus dx ft bt dbt plus 1/2 of dx squared ft bt dt. But in the meantime, I have to solve my equation. So dxt has to also be equal to mu xt dt plus sigma xt dbt, and that is equal to mu ft bt dt plus sigma ft bt dbt. Now, we won't work on the uniqueness theory for such an equations quite yet. We're just hunting for something that could be a solution. And hunting for that, well, we find that if we were to have this quantity plus this quantity, which is what's in front of the dt, equal to that quantity, and similarly, this quantity here equal to that quantity, then for such a function f, I would satisfy the equation. So we would get a solution. We would have a solution if f were to satisfy the following two partial differential equations. So first of all, I would want sigma ftx to be equal to dx of ftx. That's for all t and for all x. And second of all, I would like dtf tx plus 1/2 of dx squared ftx to be equal to mu ftx, again for all t and for all x. If I can find such an f, then such an f will indeed satisfy the equation, right? It would satisfy this equality. So let's see if we can solve this system of PD. In effect, using Ito's formula, we've reduced the question of finding a solution to the stochastic differential equation here to the question of finding a solution to this system of partial differential equation there. Now, of course, not finding a solution to the PDE will not tell me that there is no solution to the SDE. It would just tell me that I cannot find a solution to the SDE in that particular way. But for this example, we will find a solution to the system of PDE, and that will give us a solution to the SDE. Okay, so let's see if we can solve this system of PDEs. So the first one, okay, I want dx of ftx to be equal to sigma ftx. This would certainly happen if I choose my ftx of the form some function of t, let's call it h of t, times exponential sigma x for all t, for all x, and for some function h, which is c1. Right? If I have that, when I differentiate in x, I will get sigma times ftx. So this would certainly imply that. Okay, so let's look for a function of that form, and let's see if we can have a function of that form satisfying the second equation. So the second equation would tell me that h prime t times exponential sigma x, that's when I differentiate in t, plus differentiating twice in x, sigma square ht exponential sigma x would have to be equal to mu ht exponential sigma x. Again, for all t and for all x. Now, I can divide by exponential sigma x on both sides. So really, this is an ordinary differential equation for h. I'm looking for an h that satisfies h prime t is equal to mu, I forgot my over 2 here, mu minus sigma square over 2 times h of t. Now we know how to solve such ordinary differential equations. The solution of that should be h of t equal h of 0 times exponential mu minus sigma square over 2 times t for all t. Okay, so if we pick f in this specific form, so let's not call it f, let's call it g. So I'm going to define gtx equal some value at 0, so g 0, 0 times exponential mu minus sigma square over 2t plus sigma of x. So I define this certain function. It's certainly a c1 in time and c2 in x. I mean, in fact, it's c infinity in both variable. And now I have, by Ito formula, that gtbt, xt equal gtbt, which means xt equal x naught times exponential mu sigma square over 2 t plus sigma bt. This particular process is a solution to the SDE dxt equal mu xt dt plus sigma xt dbt. And we will see a bit later when we do the uniqueness theory that this solution has to be unique. So that's it. For this particular SDE, we have a explicit solution here. Okay, so let us do one last example, and we are going to look at an example that mixes the features of example 2 and the features of example 1. So I'm going to give myself two numbers, alpha and sigma, that are positive. And then I'm going to look at the SDE dxt equal minus alpha xt dt, like in example 2, plus sigma dbt, like in example 1. Right, so can we solve such an equation? Well, we are going to try using the exact same method as for example 2. So assume that x is of the form ftbt for some f. Okay, sufficiently differentiable, so c1 in the time variable and c2 in the other variable. And then use Ito formula, get a partial differential equation or a system of partial differential equations that f has to satisfy, and then find an f that satisfies that. So what does that give us? So Ito Ito's formula gives us that dxt, which is dft bt, has to be dt ft bt dt plus dx ft bt dbt plus 1/2 of dx squared ft bt dt. And this also is equal to minus alpha ft bt dt, because I want a solution to my equation, plus sigma dbt. So the system that we are trying to solve is the following. For f, a solution of, okay, so what happens in the dt component is I want dt ftx plus 1/2 of dx squared ftx to be equal to minus alpha ftx. That's for every t and for every x. And in the dbt component, I just want dx of ftx to be equal to sigma for every t and for every x. Now, what does that imply? So dx ftx equals sigma for all t and for all x really is equivalent to ftx equal sigma x plus some function of t. Okay, that's for all t and for all x. Now let's plug that in the other PDE and see what we get. So we want, when we dt that, so we get h prime plus 1/2 of the second derivative in x, which is just 0, has to be equal to minus alpha ftx, so minus alpha sigma x minus alpha ht. And that's for every t and for every x. Right, but that's bad news, because we can't possibly solve that, because this equation, will have a different solution for different value of x. And we need one solution that works for every value of x. And so this has no solution. So that's bad news. And that shows that the type of equations we're looking at, even fairly simple version of them where the mu t xt is just minus alpha xt and the sigma t xt is just a constant, even in simple cases, the hope that the solution will be a function of the time in the Brownian might well be misplaced. So if it is not of that form, then I cannot use that technique, apply Ito formula and get a PDE and solve the PDE. So what do? Well, like is often the case in ordinary differential equation, when you try to solve by hand, get an explicit method, you need to think of the form that the solution might take and then hunt for a solution that has this particular form. So we're going to try something else here than a solution of the form ft-bt. Okay, so let's try this example 3 again. I'm looking at dxt equal minus alpha xt dt plus sigma dbt. Alpha and sigma are just positive numbers, and trying to find xt of the form of a function of time in the Brownian didn't work out. So I'm going to try something else. I'm going to assume that xt is of the form of some deterministic function at times some number b naught plus the integral from 0 to t of b of s dbs, right, for some functions a and b that are just deterministic functions of t. Now, why do I think that this could be a good idea? Because if you remember your variation of constant formula for ordinary differential equation, and you think of the noise term as being an inhomogeneous term in a variation of constant formula, then the solution would indeed be of this form. So this feels like this has a chance to work, but let's find out whether or not we can make it work with functions a and b that are deterministic. Maybe that is serious wishful thinking and we should have processes here and then finding such a process will be a much more difficult task. But what we're going to see here is that we're lucky enough that the coefficients here and there are so simple that we will be able to find a solution of that form with A and B being deterministic. So let's find out what we should get. So dxt, okay, I'm going to see xt as a function of two processes. So I'm going to see axt as something of the form htyt for htx equal at times x, and for yt being, well, what's in here. So yt equal b naught plus the integral from 0 to t of bs dbs, which means in particular that dyt is bt dbt, and y naught is b naught. Okay, so let's try to find an xt of this form. Now, applying Ito formula, maybe more precisely the chain rule version of it, what do I get? I get that dxt has to be the dt part of htx, which is a prime t, times x, which is yt, and then I get that dt, plus the dx part, which is just at, and then dyt, and then plus 1/2 of the second derivative. But when I take the second derivative of this in x, I get 0, so plus 0. So it has to be of this form. Now, okay, I know what yt is. And what about dyt? Well, the yt is bt dbt. Well, I wanted to solve the equation, so I want this to be equal to minus alpha xt, and remember that xt is at times yt, and plus sigma dbt. So it seems that the condition that a and b have to satisfy, so this would have a solution, which be a solution. So this process xt would be a solution if what? If a prime of t were to be equal to minus alpha a of t for all t, and in the meantime at times bt were to be equal to sigma for all t. So can I find an a and a b that satisfies that? Well, that seems to be possible. If I take a of t to be a of 0 times exponential minus alpha t for all t, then I certainly satisfy the first equation. And then if I take b of t to be sigma divided by a of 0 and multiplied by exponential minus alpha t, sorry, plus alpha t, and divide by a of t for all t, then I do have a solution. Okay, so it tells me that the following process, xt equal a of t, so a naught exponential minus alpha t, times my y of t, so anything of the form b naught, but okay, b naught will have to be sigma divided by a of 0, plus an integral from 0 to t of sigma divided by a 0 times exponential alpha s dbs. Process of this form will be a solution. And so notice actually that in this formula the a of 0 have to cancel, so really it doesn't matter what a of 0 y was. We get that x of t equals sigma x minus alpha t plus the integral from 0 to t of sigma exponential minus alpha t minus s dBs is a solution. And of course, you could add to that any value at 0. So at 0 here, I want this term here will be 0, this term here will be sigma, so I have to add x naught minus sigma here. So this here is a solution of the equation. dxt equal minus alpha xt dt plus sigma dbt. Okay, so once again, we found a explicit formula as a standard process. So there's a dt part, which happens to be deterministic, and there is a dbt part, which is also deterministic and given by this particular function. All right, so in these three examples, we've managed to explicitly find a solution of our SDE. Now, we saw that this might be tricky because it's simple enough if xt is a function of time and O'Brien, just an application of Ito, but simple enough up to the ability of solving the appropriate PDE. It can be reasonable if x of t is of a form like this one, with deterministic processes, then it boils down to solving a system of ordinary differential equations. But in general, you might have to be extremely creative in your guesses of what the form of the process should be, and the combination of skills that come from Ito formula, solving PDE, and solving ODEs. Now, this is not very satisfying in general. This is not what people do in practice. In practice, people will just approximate the solution through a computer program. But you can only do that if you know that the solution exists and it's unique. I mean, if it's not unique, your computer approximation of a solution might be approximating a solution you don't want to your equation. And if you don't know in which space the existence exists, then you don't know which algorithm will approximate your solution to any reasonable level of accuracy. So what we need to do next, and that will be the next two videos, is to prove a theorem that guarantees existence and uniqueness of solution to this equation under as little assumption on mu and sigma as we can, and in a reasonable space of processes. Reasonable both from a mathematical point of view, that it's a large enough space so that we can solve quite a lot of equations, and reasonable from an applied point of view, as in there are good algorithms and good computer programs that you can design that will approximate solutions in that space of processes. We'll see that next.